here we see a configuration of 3 wires. And because the current in the bottom ones is in opposite direction from that on the top, the one on the top is being repelled by the 2 in such a way that the repulsive force exactly cancels the gravity. And our task is to calculate what is the requirement for the current here on the top in that case. The free body diagram of the top conductor would therefore be like this. So there are repulsive forces from the 2 conductors, and their horizontal components exactly cancel each other. So we are only interested in this vertical component, and there's 2 of them. So this angle here would be the same angle as seen from here. So that's 60, that's 30, so that also will be 30. So therefore the vertical component of 1 repulsive force Fv would be F times cosine 30. What about the repulsive force F? It is the product of the magnetic field strength at that point due to 1 conductor, and then the current I2 running in this conductor and its length L2. And the magnetic field strength due to each of these conductors is mu0 time divided by 2 pi, and the distance between the 2, that's r, and then the current in each one, so that's I1. So here we have our B due to 1 conductor, then the rest I2 and L2. So let's draw this free body diagram again. So there's the magnetic forces upwards, so there's 2 of them, 2 times F vertical, and then gravity pulling down. So we get, for the static case, that 2 times Fv must equal m times g. And what is m? That's the mass of the conductor, so we only know that it's made of copper and it has certain diameter, so we have to calculate density times its volume. So we'll get density, and the volume is cross-sectional area times the length L2. Alright, let's combine all we have so far. So we have 2 times Fv. Fv is F times cosine 30, and that equals mg. What is F? F we have here, so it's this long expression here, so 2 times mu0 divided by 2 pi r I1 I2 L2, that's our F, times cosine 30 equals mg. So now I'll express the m, pi d squared divided by 4 L2 times g. The L2's cancel. Also these guys cancel. And we were solving for I1, the current here. Oh, sorry, this is I2, and the current in these ones are I1. So solving for I2, we get rho times pi times d squared times g. And then there's stuff going upstairs, another pi here, pi squared times r. And everything else goes down. So we start with 4 mu 0 I1 and cosine 30. The density of copper is found to be 8,900 kilograms per cubic meter. Then we have pi squared and the diameter of the wire to the second power, so 1.2 times 10 to the minus 3 meters squared, g 9.81 meters per second squared, times that distance here r, so that's 3.5 centimeters, 0.035 meters, divided by 4 times 4 pi times 10 to the minus 7 Tesla meters per ampere. So that's our mu 0 I1, 50 amperes times cosine 30. So here are some, these pi's cancel, so all in all we'll get 199.5 amperes. So we need about 200 amps.